Hello everyone, and thank you for attending today's webinar, Exploiting Porosity and Density Measurements to Provide an Advanced Description of Pore Structure. My name is Jeff Kenvin, and I'm the Vice President of Science at Micromeritics and the moderator for this webinar. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. You may expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We'll try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. I'm pleased to introduce today's speaker, Tony Thornton. Tony received both undergraduate and graduate degrees from Emory University in Atlanta. Tony is currently Director of Technical Information and Senior Applications Scientist at Micromeritics and has more than 40 years of experience in the field of material characterization with Micromeritics. His expertise includes techniques for particle size, porosimetry, physisorption, chemisorption, and pycnometry, and has contributed to the development of all of these techniques and instruments here at Micromeritics. He's a fellow of ASTM and recently honored with the ASTM Kavanaugh Award for his outstanding leadership and contributions to and the promotion of international standards development. He's also a significant contributor to ISO standards. Tony, it's an honor for me to introduce you today. We're so glad you could be here to share your insights on exploiting porosity and density measurements to provide an enhanced description of pore structure.
Thank you, Jeff, for that nice introduction. I'd like to welcome all of you who have joined our webinar today, and thank you for taking the time to participate. First, I'd like to provide a brief outline of today's presentation. We're going to spend time talking about the use of material characteristics to describe objects. As an example, we'll provide multiple characteristics for an object that's familiar to all of us. Then we will look at various material characteristics that can be used to describe a porous alumina. This particular alumina is often used as a catalyst support, but realize that similar descriptions, similar characteristics can be applied to a variety of other porous materials as well, not just a porous alumina. We'll take a little bit of time to describe some of the techniques that are used to determine material characteristics for this porous alumina. You can also find additional information, additional description of these techniques by clicking on some of the links that are provided with the webinar. We'll have a look at the results obtained for the porous alumina using these techniques that we're covering today. For the techniques that provide similar results, we will compare those one to the other and take a look at which techniques maybe are a little better for some characteristics and which techniques are better for others. We'll take a look at how the combination of the results from these different techniques overlap, how they reinforce one another, how they provide a much more complete description of the porous alumina than, say, the results of a single technique would be able to provide. So what are some of the characteristics that we might use to describe a familiar object? First, we might provide information related to the size of the object, as well as the shape of the object. We might describe its color, as well as the texture of the object. And then depending on what the object might be, something like its capacity might be of interest or might be a nice descriptor. Okay, for our familiar object, let's look at some of the characteristics for a building. One of the characteristics related to size may be the number of floors the building has. So we could describe the building perhaps as two-story. And perhaps the building is rectangular in shape, or maybe a connection of a couple of rectangles together in shape. So we could describe it as a rectangular building. Okay, perhaps the building is mostly red in color. Of course, it might have windows that are a different color, but the exterior of the building we might say is red. In terms of texture, perhaps the building is made from brick. That's going to give the exterior surface a little bit of a rough texture to it. So for right now, we have a red brick building. And when we look at the usefulness of a building, often we want to know how much space is available inside it. We want to know its capacity. We might describe that as being 140,000 square feet, for example, or which would be about 14,000 square meters. So we have used some characteristics to describe our building as being a two-story, rectangular, red brick building with a capacity of 140,000 square feet or 14,000 square meters, which happens to describe the building where Micromeritics headquarters is located. And that location happens to be at 4356 Communications Drive in Norcross, Georgia, with this postal code of 30093, or as we use in the United States, a zip code. So if we were trying to locate the building via GPS or something, we would simply punch in this address. And what we would see when we got there is a two-story rectangular red brick building with the capacity given. Okay, so we looked at how to describe a building using some of its characteristics. But that's not the purpose of today's webinar. The purpose of today's webinar is to look at techniques used to characterize a porous alumina. The first of the techniques we'll look at is skeletal density determination by gas displacement using the AccuPick 3. Next, we will discuss determination of envelope density by flowing powder displacement using the GeoPick 2. Next, we will look at pore volume distribution and pore structure characterization by Mercury Intrusion Porosimetry using the AutoPore 5. And our last technique will provide determination of specific surface area and pore volume distribution by gas physical adsorption using the TriStar 2 Plus. Okay, before digging into skeletal density and envelope density, let's talk a little bit about the definition of density itself. We define density as the mass, how much, per unit volume, how big, we have of an object. So we can calculate density by taking the mass and dividing it by the volume. Now the mass of an object is usually pretty simple. It's easy to determine. We put it on a balance, it gives us a number, we have the mass of the object. The real question becomes, what volume do we assign to the object? What is included in that volume? And so the various densities that are available that people talk about, that people calculate, mass is always the same. What's different is the volume. Okay, so let's consider our object of interest. Here in the little cartoon on the left-hand side, we have a three-dimensional representation of an object. We see solid material and what looks like some empty space in there. And then on the right-hand side, we see a two-dimensional projection of that object. Okay, so that raises the question, what is the volume of our object? And that's what we're going to discuss here with the different techniques used to determine the different types of densities, where what is included in the volume of the object varies with the definition, varies with the type of density we're trying to determine. First, we'll look at the determination of skeletal density using gas displacement. Now, sometimes you'll hear people refer to the absolute density or the absolute volume being determined by the gas displacement technique, and sometimes it is, but not always. Sometimes the skeletal density value is not necessarily the absolute density value. For example, in the situation where there might be something we call closed porosity. We'll mention that again in just a moment. As we said, we determine the skeletal density by determining the skeletal volume using the technique of gas displacement pycnometry. We surround the sample in a calibrated container with a free-flowing gas. Now, the gas molecules are able to enter into any open porosity, so the volume of the open pores is not displacing gas. So what we have is the volume of the object less any open porosity. Now, we can calculate a skeletal density from that skeletal volume, and if there are no closed pores, we might say that that gives us the absolute density. However, if there are closed pores, pores that cannot be filled from the outside by the surrounding gas, then the volume of those closed pores is included as part of the skeletal volume of the solid object, along with the part that is solid, and therefore our calculated skeletal density will not be equal to the absolute density because of the presence of the closed porosity. Now, the gas displacement technique is based on a description provided by Archimedes back around 250 BC, where he described a technique for determining the true volume of a material with an irregular shape by measuring the volume of a fluid that it displaces. Now, oftentimes people think of the Archimedes technique where the fluid is a liquid. However, the fluid can easily be a flowing gas, just as we see in the determination of skeletal density by gas displacement. So let's describe a second density, that being the envelope density we determine by a powder displacement. Here, instead of small gas molecules surrounding the sample and penetrating pores, we surround the sample with a dry, free-flowing powder that is fluid-like in its behavior, and it then surrounds the object. Unlike with gas displacement, however, due to the size of the particles that make up the powder, they're not able to penetrate the small pores in the object, and so now our envelope volume is defined as being the volume of the solid object plus the volume of the pores that cannot be filled with the flowing powder. So this gives us an envelope or a bulk volume that is used then to calculate an envelope or a bulk density. The difference between the envelope volume and the skeletal volume being the pores that the gas could fill, but that the powder could not. Okay, for our third displacement technique, we will be displacing a fluid by the sample. In this case, we're going to be surrounding the sample with mercury. Now, mercury porosimetry usually is used primarily to determine the total pore volume and the pore volume distribution of a material, and we will be including that in our characterization of our porous alumina, but we also have the extra benefit of being able to determine some densities using the mercury porosimetry technique. If we happen to know the empty volume or capacity of our sample chamber, we call those a penetrometer, then we can determine the bulk volume of the sample and the skeletal volume of the sample under test, and from those we can determine a bulk and skeletal density. First, we're going to describe the determination of envelope or bulk density using the technique of mercury displacement. Now, we define density as mass divided by volume, so our task with mercury displacement is to determine the bulk volume of our material in order to calculate a bulk density. Now, the bulk volume is the volume of the material after any very, very large open pores have been subtracted. And that subtraction is done by the fact that when we surround the sample by mercury, some of the very largest pores might be filled with mercury and so are not displacing mercury. In our displacement techniques, the volume of the object is equal to the volume of the fluid being displaced. When we fill the penetrometer with mercury to surround the sample, we do have to apply a small amount of pressure. And that very small pressure might result in pores larger than, say, somewhere around 180 micrometers or so. But those pores are already filled with mercury at the start of the analysis, and so their volume is not displacing mercury. Their volume is not going to be a part of the bulk volume of the sample. The bulk volume will be the volume of the solid material plus any pores not filled at that initial pressure. And so we calculate the bulk volume of the sample by taking the known volume of the penetrometer and subtracting from it the volume of mercury that was used to fill the penetrometer without yet filling those remaining open pores. We determine that volume of mercury surrounding the sample by knowing the density of mercury from the temperature of the analysis and by knowing the mass of mercury that was added to the penetrometer containing the sample. Now we define the skeletal volume again to be the volume displaced by the material itself after we have filled the pores. Now, we're not going to be able to fill the smallest pores in the sample if they're smaller than about 3 nanometers or 0.003 micrometers, because we just can't get the mercury into there. And we'll talk a little bit more about that later. But so basically the skeletal volume now is going to be the volume occupied by the solid material itself and perhaps some very small pores. Over the course of the mercury intrusion experiment, we will progressively fill smaller and smaller pores by applying higher and higher pressures to the mercury. Mercury will fill the larger pores first because it is easier to get the mercury to go into those pores, and it will fill the smaller pores later as we go to higher and higher pressures. Once we have reached our highest pressure, we will take the total pore volume determined at that point, subtract it from the bulk volume that we determined from the filling pressure to get a skeletal volume for the sample, and from that, of course, be able to calculate skeletal density. For our fourth material characterization technique, that of gas adsorption, we're not going to be determining density. We're going to be determining the surface area and the pore volume distribution of our porous alumina. The amount of gas adsorbed by the sample is a function of the gas pressure over the material, as well as the temperature of the sample. Sample temperature is controlled by immersing the sample in a sample tube into a cryogenic liquid, typically liquid nitrogen. At low gas pressures, some of the molecules will start to adsorb onto the sample, beginning the formation of a first layer, as we see in illustration A. In illustration B, we see the formation of a first complete layer of gas molecules on the surface of the sample. We can use the monolayer capacity, the amount of gas to form that one layer, if we know the number of molecules in it and we know the area occupied by a single molecule. Now in practice, the first layer, the monolayer, doesn't form initially before other gas molecules start to adsorb into a second or a third layer. However, there are data reduction techniques available to us, such as that of Brunner, Emmett, and Teller, the BET method, where we can determine the monolayer capacity from the way in which the multiple layers are adsorbing onto the sample. As we continue to increase the pressure of gas molecules over the sample, we'll have additional layers continuing to form, and we will start filling some of the pores completely. And so from these additional data points, we start to build up the pore volume distribution as we see at illustration C. We continue the process until we reach a pressure that equals the saturation vapor pressure for the analysis gas at the analysis bath temperature, at which point we have all pores filled and even start to see some bulk condensation over the top of the sample at illustration D. Okay, we've described the 4 techniques that we're going to use to characterize our porous alumina. Now let's take a look at some results. First, we see here the skeletal volume for 6 aliquots of our porous alumina. Now, each analysis involved 10 test cycles, and so we see cycles 1 through 10 results here for the 6 alumina samples. 3 of those, for samples 4, 5, and 6, we see values a little bit less than maybe 0.09 cubic centimeters. Very close agreement between the samples, very nice repeatability. For the other 3, we see values of about 0.25 cubic centimeters, that being for samples 7, 8, and 9. Now, okay, wait a minute, we're characterizing different aliquots of the same material, and yet we're measuring different volumes. Okay, let's take a closer look at the material that was under test. For the first 3, for aluminas 4, 5, and 6, we characterized about 0.27 grams of material. And then for aluminas 7, 8, and 9, we had about 0.83 grams of material under test. So we had more material under test for the last 3 than we did for the first 3. Now remember, we want to determine skeletal density. And skeletal density is the mass divided by the skeletal volume. So when we look at the skeletal density for the 6 aluminas, we see there's very good agreement between them. The reason we had that grouping of 3 with a low volume and 3 with a high volume is because we characterize different masses of material. But once we take into account that fact, we see again very nice agreement. Now when we had more material under test for 7, 8, and 9, we had a little bit better repeatability of the cycles than for the smaller amount of material. And that's generally the case with gas displacement pycnometry, that the more material you have under test, generally the more reproducible and repeatable the results. We also recorded the temperature of the analysis for each cycle, and we see here that for all of these, they're within about 0.002 degrees of 20. 20 was our set point for the analysis, and then again we have very good temperature control. This does help to improve the repeatability, improve the reproducibility and accuracy of the results to have good temperature control. All right, let's look at a summary of the skeletal density results then for samples 4 through 9 as determined using the AccuPick 3. We see here in the first column the sample identifications. We see in the next column their volumes, and we see that grouping that was obvious from the plots that we saw. But if you look at the third column there, skeletal density, we'll see that all of them were very, very close in value. The average of all of the tests is 3.366 grams per cubic centimeter with a standard deviation of 0.008. Now, the value shown for each of the aluminas, that is the average of the 10 test cycles. And then we can average together the results and look at their repeatability and reproducibility. We show the sample masses in the last column, and of course the temperatures all were right at 20 degrees. Next, we'll take a look at envelope volume determined using the GeoPick 2. Here we selected 3 of the previous samples, samples 4, 5, and 6, and again determined their envelope volume for 10 cycles. We see a little bit of difference between the 3 samples. From about 0.29 to about 0.33 cubic centimeters. Again, though, we're talking about volume. Now, once we look at the envelope density, where the mass under test is divided by the envelope volume determined, we see much closer agreement between the 3 samples. As a matter of fact, the slight variability between tests pretty much overlaps on these. So we have values from about 0.89 to just over 0.91 grams per cubic centimeter for the envelope density. In the table on the right now, we see the summary of results for envelope density determination of alumina samples 4 through 6. What we see for each alumina again is the average of the 10 test cycles. We see that variability in the envelope volume that we explained because we had different amounts of material under test. So when we look at the envelope density column, we do in fact see that we have an average of about 0.906 grams per cubic centimeter with a standard deviation of 0.006 grams per cubic centimeter for these 3 samples. We do have the ability now, since we have the skeletal volume, since we have the envelope volume, we can look at the difference between those and determine a pore volume per gram of sample. And for that, we have about 0.0807 plus or minus 0.008 cubic centimeters per gram of total pore volume. And since we have the bulk volume and we have the pore volume, we define porosity as pore volume divided by envelope volume, so we can calculate the average porosity for these, and we see that it's about 73% porosity. Now for these samples, we had about 17 of the little pellets you see here under test. They're mostly spherical in shape. Now the way in which the dry flowing powder that we use to determine displacement packs around these is related to the size and the shape of the material. We do have conversion factors for converting displacement into volume, but again, the actual value depends a little bit on how the powder packs around the sample. So if we want to improve our results, then we may want to calibrate that packing process if we can characterize materials of known volume. In order to calibrate our conversion factor for small, roughly spherical beads, we analyzed 17 3mm glass spheres. These glass spheres are non-porous. So we would expect, since they're non-porous, for their skeletal volume and their envelope volume to be the same. So if we knew the skeletal volume of these, we could characterize them with the geopic using the dry flowing material, and we could come up with a conversion factor that would equate the envelope volume to the known skeletal volume of these beads. Since they're about the same size as our porous alumina, since they're the same number of beads, then we would expect the dry powder to pack around these the same way they would our material under test. Obviously, we can determine the skeletal volume of our 17 beads using the technique of gas displacement, which we've done. The average of the 10 test cycles, 0.2411 cubic centimeters. The resulting skeletal density when we use the mass of the glass beads was 2.5296 grams per cubic centimeter. We can use these values then with the results from the geopic to calculate a conversion factor that we can use with our roughly spherical alumina samples so that we get reliable results for envelope density of our porous alumina by calibration using the glass beads. So from the skeletal density analysis using the AccuPic and the envelope density analysis using the geopic, we were able to combine the results and determine a total pore volume and a percent porosity. We're going to move to our third technique now, that of Mercury Intrusion Porosimetry, where we're not only going to determine pore volume and porosity, as well as a bulk and a skeletal density, but we're going to look at a pore volume distribution. We're even going to be able to calculate a pore area from that distribution. So we see Mercury Porosimetry as a very versatile technique. Now, what we have here are intrusion and extrusion analyses for 6 of the alumina aliquots. We start at a pressure of about 4 pounds per square inch absolute, moving along the bottom of the curve, the lower curve, from left to right as we increase pressure, and we see intrusion start to take place just above 1,000 pounds per square inch. continuing up and leveling off before we get to the maximum of 60,000 pounds per square inch. Once we finish the intrusion cycle, we reduce the pressure, and we see the upper curves now. We move backwards in pressure. The intrusion, the amount intruded starts to come back out. We have extrusion of mercury from the sample, though notice when it levels off, it does not level off back at zero cumulative intrusion. So some of the mercury is retained by the sample, even when we reduce down to pressures as low as about 1 atmosphere. We're going to make use of that trapped mercury that does not extrude, to look a little closer at some pore structure later on. Here we see a slightly different depiction of the mercury intrusion and extrusion data for our 6 alumina aliquots, where on the y-axis we still see cumulative intrusion, but on the x-axis we have the pore size given in nanometers. By using the surface tension of the mercury and by using the angle of contact between mercury and the surface of the sample, we can calculate from pressure an equivalent pore size, the size of a pore opening being filled by the mercury. And that pore opening size, or pore size, that corresponds to a pressure is one of the explanations for the hysteresis seen, the different path taken by the extrusion, where it is believed that is related to cavity sizes, where we have small pore openings filling larger cavities behind them, kind of like the doorway into a room. That is one explanation for the hysteresis, and it's a fairly reasonable one, often used type of explanation. By the way, take a look in the curves there. We see this one purple curve for alumina 2 that doesn't quite match the others. And we're going to talk a little bit about that in the next slide. But notice it follows a slightly different path, doesn't quite show as much total intrusion, doesn't show as much extrusion either. It looks like there's more mercury left inside the sample. If we take the derivative of the cumulative intrusion curves, we see here the log differential intrusion. It kind of gives us an idea of the shape of the curve. It shows us the pore size at which there was the most mercury filling the modal diameter there. And again, look at our purple peak. It's shifted over slightly to smaller sizes. There's not as much area under the curve. It shows a bit narrower distribution. The reason for this is it was characterized using a slightly different method than the others. The other 5, we used a technique called equilibration by rate of intrusion. We held the pressure constant and waited for the mercury intrusion to stop to make sure any long, narrow, tortuous pores were filled completely before moving to the next pressure. If we'd moved on to the next pressure while a pore is still filling, part of its volume would have been assigned to the higher pressure, part of its volume would have been assigned to a smaller diameter. And that's what happened with alumina 2. Alumina 2 was analyzed using a fixed 10-second equilibration interval. This is very common in mercury porosimetry, very common. But as you see, it doesn't always give quite the same answer as waiting for equilibration to completely finish. So that's why curve number 2 doesn't quite match, or for alumina 2, doesn't quite match up the others. Here we see a summary table of just some of the parameters that can be obtained from the mercury intrusion analysis. People tend to summarize the data different ways. By the way, notice there's 7 analyses here shown here. Alumina 8 is included. During the analysis of alumina 8, the extrusion analysis portion did not complete due to a power failure. So I did not include its curves. It is included here in the statistics, which are taken from the intrusion portion of the analysis because it did complete the intrusion process. But we can see here, if we look at alumina 2, its total pore volume shown in that second column is a bit lower than the others. We see if we go all the way over to column 4, its porosity, it's pretty close to the others. But if we go all the way over to, say, the next to the last column, we look at its average pore diameter, it is a bit lower. And its modal diameter in the third from the right column is very much lower. So we do see the impact of the equilibration. But even with that, we see very good reproducibility In the total pore volume average is 0.760 plus or minus 0.008 cubic centimeters per gram. In the first column, we see very good repeatability of the porosity, 72.64%. Notice the bulk and the skeletal densities. They are not as reproducible as that from the gas displacement. We're going to talk about that a little bit more. Median pore diameter, the 50th percentile, very good reproducibility. The modal diameter there, again, very nice reproducibility. You do see we characterize two different masses here. Now you'll see what happened to samples 1, 2, and 3, why they did not go for analysis by the geopic is because the mercury test is a destructive test, but so is the geopic. It leaves the sample slightly contaminated with the flowing powder. Okay, well, let's compare density and porosity results from our three techniques: Mercury Intrusion Porosimetry, gas displacement pycnometry, and the solid medium flowing powder displacement pycnometry. First, let's take a look at skeletal density by the Mercury Intrusion Porosimetry and the gas displacement pycnometry methods. We see a little bit of difference, 3.555 versus 3.366, but also much better reproducibility by gas displacement. The calibration of the gas pycnometers is very accurate, very reliable, very robust. The determination of skeletal density by mercury intrusion is based upon knowing the volume of the mercury that fills the penetrometer when it's empty. And there's not as much reliability in that result. There's a little more uncertainty because when we determine that calibrated pin volume, we're measuring the mass of mercury that it holds, and we're using a density to calculate a volume, and sometimes we don't know exactly the temperature of the penetrometer. In addition to that, there is some heating going on of the mercury inside the penetrometer during the analysis, which impacts the density. The mercury may not have the same density at the end of the analysis it did at the beginning, so there's just more uncertainty there. Comparing the bulk or envelope density from mercury intrusion and our flowing powder displacement, reasonably good agreement. Now remember that we calibrated the envelope density results by using the glass beads, the volume of which we had determined using gas displacement. So we would expect, a reasonably good calibration there. The mercury intrusion bulk density suffers from the same uncertainty in the penetrometer volume that the skeletal density did. Matter of fact, the skeletal density is calculated from the bulk density. Looking at the percent porosities, we do see reasonably good agreement between the two. Again, the two displacement techniques give a little bit better reproducibility than the mercury intrusion, again, due to some of the uncertainties in the penetrometer volumes. Now, some of that uncertainty cancels out because that uncertainty is in both the bulk density and the skeletal density measurements from mercury intrusion, so some of it does cancel out, so it does improve things. And actually, our percent porosities agree quite well between the two methods. Comparing the total pore volumes, there is some difference there. One of the things about mercury intrusion is we very, very carefully determine the intrusion volume based on some very careful measurements of capacitance converted into intrusion volume. So those pore volumes are definitely more reliable than looking at the way a flowing powder packs around the lumina beads. So yeah, there's a little bit of difference there, and in this case the mercury intrusion is the better of the two values for intrusion volume. Okay, let's have a look at results of our fourth analysis. This is nitrogen gas adsorption onto the 6 alumina aliquots. The samples are characterized at liquid nitrogen temperature by using a cryogen bath. The results are shown as the quantity adsorbed versus relative pressure, where it's the absolute pressure divided by the saturation vapor pressure of the gas. We can't go to higher than the saturation vapor pressure, it just forms liquid nitrogen. The curves to the right hand side there at the higher pressure, that's the adsorption branch, and then to the left hand side is the desorption. Much like with mercury intrusion, the two branches are related to the sizes that are being filled. In this case though, for nitrogen, the adsorption is generally speaking assigned to the cavities and desorption assigned to the throats. Now remember, in intrusion was assigned to the size of the throats. Desorption is assigned to the size of the throats, so we might think those would be comparable. All right, so we see here the calculated pore volume distributions for aluminas 1 through 6 from the adsorption branch of the isotherm. This showing the cumulative total pore volume found in pores smaller than the current diameter. And here we have the log differential distribution, basically the first derivative of the cumulative curve. Notice the modal diameters are up around 18, 19 nanometers in size. And now we see the results from the desorption branch of the isotherm, where we calculate the pore volume distribution, showing here the cumulative pore volume found to be in pores larger than the current diameter. Taking the derivative of the desorption cumulative distribution, we see the log differential. Notice here that the modal diameters are probably somewhere around 12 or 13 nanometers, whereas from the adsorption branch we're around 18 to 19. And again, we say the adsorption gives us information about the size of the cavities, while desorption gives us information about the size of the throats. We see here the statistics from the physisorption analysis of our 6 aluminas using the TriStar 2 Plus. Again, lots of different statistics we can look at. One of the things we can look at is the VET surface area, about 183 meters squared per gram. We can look at those two modal diameters from the second to the right, next to the last column there. We see the modal diameter from desorption is around 12 nanometers. If we move over a few columns there, a couple of columns there, we see the modal diameter from the adsorption to be about 18. So we do see that difference in results. Again, we can look at a lot of these different statistics, depends on what people want to use. They're often looking at pore size, they're looking at average pore size distribution, and surface areas are the most common. And again, we see the sample masses here. We used about 0.27 for all of them. I mentioned earlier we might be able to compare intrusion data to desorption data. And we see here the results for alumina 1. In red we see the mercury intrusion analyses, and in blue we see the gas adsorption analysis. Looking at the respective log differentials, we see that the modal diameters do line up nicely. Now, there's a little bit of difference in the scaling here because we have more data points in the mercury intrusion analysis than in the gas adsorption analysis. That's why the shapes of the peaks are a little bit different, but notice how well the modal diameters do line up. By the way, that is one way we can help to determine the contact angle for mercury intrusion. That contact angle is dependent on the material and its surface characteristics, its surface energies, and so forth. The gas adsorption data is not that dependent on the material surface. So the gas adsorption data tends not to be a function of the material surface specifically, whereas mercury is. So we can use the gas adsorption data to calibrate the contact angle. And that's exactly what I did for this sample. I determined I needed to use a contact angle of 138 degrees. So that I got this really nice correspondence between gas and mercury results. Okay, let's take a closer look at a comparison between the gas adsorption data and the mercury intrusion data. Okay, first let's compare total pore volumes. 0.76 on average for the analyses of the mercury intrusion samples, about 0.72 for the gas adsorption results. Small difference there, probably just typical of comparing two different techniques for measuring a similar property. So we would still call that good agreement. And now for the not so good agreement. We see total pore areas are much higher than the VET surface area, that calculated from mercury intrusion compared to gas adsorption. With mercury intrusion, we calculate the pore areas from the pore volume distribution. We look at the volume of mercury moving into the pore at a particular pressure. We calculate a diameter for the pore throat, and we assume that all of the volume is going in to a cylinder that has the diameter of that throat. We don't have information about the cavity behind it, so we calculate the areas to be the area of a cylinder, where we take 4 times the volume and we divide it by the diameter. We know that we have cavities of different sizes from the throats, from the hysteresis we saw in gas adsorption and the hysteresis we saw in mercury intrusion versus extrusion. So we know that that value is not correct. The BET is far more reliable as a measure of surface area than the calculated mercury pore area. Okay, let's take a look at the average pore diameter. Now, the average pore diameter is what is the diameter of a cylinder that could have the total pore volume and the total pore area is found. Now, we know that the pores are not cylinders. So, neither one of these is necessarily that reliable of a value. Mercury porosimetry probably less so because we know that its total pore area is not as reliable as the BET surface area. Now, when comparing the modal diameters from the desorption and from the mercury intrusion, we saw in the plot of the log differentials that they agreed quite closely, and here we see that they do, 12.07 versus 12.76 nanometers. Now, previously we had a webinar where we talked about a new method for determining more information about the pore structure and isolating the volume of mercury filling the throats versus that filling cavities through throats of different sizes, our high definition intrusion cycling. And we're going to basically take advantage of the mercury that is not extruded when pressure is reduced. For this method, we start the mercury intrusion analysis as we normally would, but we only intrude up to about 5% of the total pore volume. We then extrude back to near atmospheric pressure. Recall, some of the mercury does not extrude from the sample. We'll start a second intrusion cycle, refilling the mercury that did extrude and continuing to add an additional, say, 5% of the total intrusion volume. We will extrude back to atmospheric pressure, then start another cycle, adding another 5% of the intrusion, extruding that again, and continuing this addition of 5% increments until we reach the total intrusion. Here we see results from the first 7 of 20 cycles that were performed on alumina aliquot 10. The blue data is the first cycle. We see intrusion, and then we extrude the single point. In the orange, we see the second cycle, where we add additional points and we extrude back to atmosphere. Green is the third cycle, red the fourth cycle, then purple, then brown, then the pink. Each one of these we're adding an additional 5% of the total intrusion. It is the difference between these flat regions where we're seeing data collected at the same total pressures, and we're looking at the amount of mercury that did not extrude that is going to give us the additional information related to the volumes that are filling into chambers that is not extrudable through different pore throat sizes. And now we see the results for all 20 of the cycles. So let's take a look at the data that we can extract from this. We now can separate the intrusion data into the reversible intrusion, which basically is the reversible filling of the throats, the volume in the throats shown in orange for the log differential and in green for the cumulative, from the volume filling the cavities that is irreversible. We don't know the size of the cavities. We do know the size of the throat through which that volume was being filled. The log differential shown in blue and the cumulative shown here in red. So looking at the summary data, we see that we completed 20 cycles. We did use a contact angle for 138 that we determined earlier. We separated the total pore volume into that filling cavities irreversibly at about 0.2 cubic centimeters per gram and filling the throats at about 0.57 cubic centimeters per gram. The pore throat median diameter, 12.5 nanometers, matches very, very closely to that by gas adsorption. Using the pore throat distribution and not that irreversibly filling cavities, we can do a better job of calculating a pore throat area based on our assumption of nearly cylindrical pores, and we get a value of 183.87 when doing so. And see how well it matches the average value we got for the BET surface area of 183.56. So we definitely have two improvements here with a high definition intrusion cycling. We get a much better estimation of the pore throat area, and we get much more information about the volume of the cavities in the throat sizes through which they're being filled. Okay, let's do a comparison of results from the different techniques. We'll start with those that gave us density for the alumina samples. We saw that the gas displacement yielded better reproducibility and reliability compared to that from mercury intrusion for skeletal density. The flowing powder displacement and mercury intrusion yielded similar results for bulk and envelope density, but there was slightly better reproducibility with the flowing powder displacement. Okay, let's look at total porosity of the alumina samples. Mercury intrusion and combination of gas and flowing powder displacement gave very similar porosities for the aluminas. For total pore volume of the alumina samples, all the techniques yielded very similar results: mercury intrusion, gas adsorption, and the combination of the displacement techniques. For pore volume distribution of the alumina samples, mercury intrusion and gas adsorption analysis yielded very similar results, especially when we compare the mercury intrusion data with the gas desorption data. For total surface area of the alumina samples, the traditional mercury intrusion analysis gave us significantly larger calculated total pore areas than we got from the BET surface area determined by gas adsorption. Now, with the high definition intrusion cycling, the mercury intrusion total pore area just for the throats was very similar to that from gas adsorption BET surface area analysis. So we must ask the question, which technique is best to characterize a given material? It is the one or more than one that best predicts the material's behavior. Two techniques are going to be better than one. Three techniques are going to be better than one. Some are going to be better with some parameters than others, but they're all going to build a more complete picture of the sample that we have under test. So just to summarize, we talked about the use of material characteristics to describe an object. We started with an example of using multiple characteristics for a familiar object. We gave a description of a building, the building where Micromeritics headquarters is located. We then discussed material characteristics that could be used to describe a porous alumina catalyst support. We described the techniques that could be used to determine those material characteristics. We discussed the results obtained with those techniques and compared the results from the different techniques with one another. We then discuss ways in which the techniques can support one another, they can corroborate results, they can help improve results by providing additional calibration information and additional adjustments for things like contact angle and conversion factor for the dry powder displacement method. And here we can see where these methods fit within the Micromeritics portfolio. We used the TriStar 2 Plus for surface area and pore volume distribution. We used the AutoPore 5 for total pore area calculation, for pore volume distribution, and for porosity. We used the AccuPick 3 to give us the skeletal density. We used the GeoPick 2 to give us the envelope density. The combination of those gave us porosity. Of course, the AutoPore also gave us bulk and skeletal density values as well. I'd like to thank everyone for attending this afternoon. Please stick around. It'll take a few seconds to load up the question and answer session. So again, please stand by.